Welcome to lecture 20. In this lecture, I want to talk about weak departures from Minkowski space. Recall that in lectures 10 and 11, we derived the geodesic equation, which is given here as equation 20.1. It involves the second derivative with respect to proper time of the coordinates, and then it involves the first derivative of the coordinates times the Christoffel symbol. What we want to do in this lecture is that we want to consider the geodesic equation in a particular limit, namely in the non-relativistic limit, meaning the Newtonian limit, where we take the spacetime to be nearly Minkowski and the speeds to be small. So basically, we have a metric tensor G mu, from which we derive, for instance, the Christoffel symbol, and we take G mu to be almost Minkowski. And in addition, whenever we find any kind of speed, we take the speed to be much, much less than the speed of light. The first step is that we rewrite the geodesic equation, noting that the first derivative of the coordinates with respect to proper time is something like a 4 velocity. I call this 4 velocity u alpha, and any 4 velocity can always be written in the following form. So I have something that is a 4 vector where I have a unity in the time-like direction, some usual 3 velocity in the space-like direction, and a gamma factor in front. Now, I said that we want to look at the non-relativistic limit, meaning that speeds are much, much less than the speed of light. So that means that v here will be much, much less than 1. So the gamma factor can be approximated by 1. And to leading order, I can also neglect the v here. So that means that in this limit, limit where v is much, much smaller than 1, the 4 velocity just becomes a vector that is pointing in the time-like direction and has a 0 in the space-like direction. This means that since u alpha is the derivative of the coordinates with respect to proper time, if u alpha only has a non-vanishing component in the 0 direction, this means that also dx0 by d tau is the only non-vanishing derivative. So this is the only non-vanishing derivative. So that means that this contraction between the Christoffel symbols and the derivatives of the coordinates only get entries where alpha and beta are equal to 0, because the other ones, for the other ones, dx alpha by d tau is just vanishing. Next, we want to approximate the metric to be near Minkowski. We do this by writing G mu in terms of the Minkowski metric, which is just a diagonal metric in 4 dimensions, which has a -1 in the time-like direction, plus a term which we call h mu nu, which is a 4x4 matrix that is supposed to be small compared to these leading order Minkowski metric. In addition, what we want to assume is that this deviation from the Minkowski metric is also static, meaning that it's independent of time and can only depend on space. Given any metric, we always know how to calculate the Christoffel symbols from the derivative of the metric. We can do this for this metric here, and because I'm lazy, I have used my computer program to do this. I will upload the corresponding Mathematica file to let you check the individual steps for this. The main message is that once you plug this into the computer and use the symbolic manipulation program, you find that the relevant Christoffel symbol, gamma mu 0, 0, is given by -1/2 times a 4 vector, which is 0 in the time-like direction and has the gradient of the 0, 0 component of this function h here in the space-like direction. So if we plug this in to the geodesic equation, then we find that in a non-relativistic and near Minkowski limit, we get for the geodesic equation in the direction, or for index mu is I and mu is 0 respectively, this is the this is the geodesic equation where I have set mu is equal to I, so the space-like index, and this is the geodesic equation where mu is equal to 0, where there is no contribution from the Christoffel symbols. Clearly, since the second derivative of x naught with respect to proper time is vanishing, this just means that dx0 by d tau, the first derivative, is just a constant. We'll take the space-like parts of this, and we want to rewrite, in particular, the second derivative of the space coordinates with respect to proper time as follows. We first write it as the first derivative of the first derivative of the coordinates. Then for this inner product, we basically rewrite, for the outer product, we basically first rewrite the derivative with respect to proper time as the derivative with respect to x0 times the chain rule dx0 by d tau. And then we do the same thing for the inner part here. So we rewrite dx vector by d tau as dx vector by dx0 times dx0 by d tau. Now, I said that this condition implies that dx0 by d tau is constant, so we can pull this term out of the derivative, and we find that we have dx0 by d tau squared times dx0 dx vector by dx0. So this is this term here if I denote x0 by tau, by t. And then the dx0 by d tau squared is precisely the same term that is appearing over here. So that cancels out of the geodesic equation for the space-like parts. So this equation, using this rewriting, then turns out to be an equation like this. A second derivative of the coordinates is equal to 1/2 times the gradient of this function h00. So what that says is that we have the second derivative of coordinates with respect to time is equal to something. That something is a gradient. And the second derivative with respect to time is an acceleration. So this equation says acceleration is equal to the gradient of something. That certainly might look familiar if you want to think about your undergraduate physics courses. In particular, we have Newton's law that says that the acceleration in a system that sort of has gravity is equal to minus the gradient of the gravitational potential. So phi here denotes the Newton's gravitational potential. And if you compare these two equations, then you find that the geodesic equation in the non-relativistic near Minkowski limit gives Newton's law if we identify the gravitational potential to be minus 1/2 times this function h00. We can, of course, rewrite this by saying that, okay, this is just the deviation of the metric from Minkowski. So that means we can write down the actual metric in this limit, the metric component g00 in this limit, as -1 plus twice the gravitational potential. So if we set the 0,0 component of our metric to be -1 plus twice the gravitational potential, our geodesic equation will encode Newton's law that the acceleration equals minus the gradient of the potential. Of course, this is all taken to be in the weak field limit, where phi is much, much less than. This already summarizes this lecture. So we started out with the geodesic equations, and we considered weak departures from Minkowski space. We found that the geodesic equation turned into the Newton's law if we identified the metric component g00 and the Newton's gravitational potential through this equation that we had on the last slide. That is already half the information we need to sort of write or make the connections between the field equations we have been talking about in the last lectures and a generalization of Newton's law of gravity. And we'll explore those consequences in the next lecture.